Can you hear me now, everybody?
Yes, we can.
Yes.
Thank you. Thank you for waiting. I really apologize that it's very unfortunate today. Traffic holds me. So I thank you, those of you who delivered the message on behalf of me. I'm here now. So what I'm planning to do is just go ahead straightly to the review guideline, which I have posted for you. During the discussion, I want you to take some notes, and then I'm going to send you the upgraded version of the review guideline, the one that we will be working here. So this is just to be clear for you, just to give you an idea that this is like the whole picture or the GPS of what the final exam would consist of. What are the main components that you will see in your final exam. So this is like a skeleton or a structure for you. What type of questions are expected? The questions are just like the previous questions will be on a lockdown browser. They either be multiple choice questions and a true false questions. And what I'm listed right now are the items that's going to be the items that are discussed here will be the part of the final exams. So having said that, if down to the line, if you have questions, please raise your hand and then ask me questions, please. So the first thing that I would ask you is know the difference between electrolytes and non-electrolytes. In order to answer this question, you should know what an electrolyte is. First of all, an electrolyte, they are compounds. They have to be dissolved in water, and they should form ions. So I provided some example here, like HCl, which is aqueous. HCl is hydrochloric acid. When it's decomposed in water, it forms ions, so it can be an electrolyte. Rubidium sulfate is ionic compound. It's composed from rubidium and sulfate ion. When it's decomposed, it forms ions, so it can be an electrolyte. C6H12O6, that's glucose. Glucose it can dissolve in water. However, it is a non-electrolyte because it's organic compound and it will not form an ion. So please make sure that if something is dissolved in water, that doesn't necessarily mean it's an electrolyte. You have nitrogen here. Nitrogen is a gas, you see. So nitrogen is a gas, will not be considered as an ion because it doesn't have a positive and a negative charges here. So let me see, I have two people are waiting. I hope they are here. Okay, and then also be careful about the status. For example, we have sodium chloride S, which is solid, sodium chloride aqueous. Which of the two would you think would be an electrolyte? Sodium chloride S, sodium chloride aqueous. So the sodium chloride S, because the status here is a solid, so it cannot be an electrolyte. But if it is an aqueous means that it forms a positive and a negative ions, then it can be an electrolyte. So the status is very important. So that's how we identify whether the compound is electrolyte or not. So the next thing that you would also expect is how do we know the compounds are soluble in water or not soluble in water? So the solubility guideline would be provided. We discussed about solubility guideline in chapter 4. The only thing that's expected from you is how you can able to read the solubility guideline, and based on that you can answer like questions like ionic reactions and the net ionic reactions. Okay, also that you can able to identify spectator ions as well, spectator ions. So also I want you to see all types of reactions. You can learn it from chapter 3 and chapter 4, um, which is like ionic and net ionic reactions, combustion reaction, uh, combustion reaction, precipitation reaction, oxidation reduction reaction, um, decomposition reactions, single reactions. Make sure that know what is the type of reactions. So like I say, it's going to be a multiple choice question, but you need to identify, you need to find out the types of reactions that you learned during the course of the semester. Uh, Also, like, how do you know here rubidium sulfate is soluble in water, calcium carbonate is insoluble in water? So you will have a solubility guideline. You can use solubility guideline as a reference. However, that you need to know which one is soluble and which one is not soluble in water. So solubility guideline also discussed in the lecture class. It also discussed in the lab class. I don't think you will have a problem to identify solubility guidelines or identify compounds that are soluble or insoluble in water. Um, so like if you see chemical reactions, it's not only enough to uh, identify the types of chemical reactions, you also need to know whether they are, whether they have to be balanced. Balancing the equation is very important. So we need to learn how to balance an equation. Um, they have been, but they have to be, uh, they have to be,
You don't know my name.
but they have to
But
be
check on
balanced.
the
Okay, you
telephone.
need to know balancing the equation. Now, when a polyatomic
Bruno, come
ions
on.
are involved, polyatomic ions are involved, it's also important to, as a tip, I would like to tell you that if you have a polyatomic ions like nitrate, you would always start with
Téléphone à Zoom.
uh,
Za question vraiment. Sio kama mtu nakomea ngwa.
all right, okay. Okay, please, if mute your mic, guys. If you are on mic, you mute your mic. Try to mute your mic, please. So if you have to balance the equation, start with the polyatomic ion first. For example, we have silver nitrate reacts with magnesium chloride. You have silver chloride and magnesium nitrate. Here you have nitrate. Here you have one nitrate here. You have two nitrate here. So you see, because of you have two nitrate here, you're going to put two here. That way you can able to balance. And the rest, once you start balancing the polyatomic ions, the rest you can balance it just by counting the numbers. Like you have two chlorine here, maybe you can put two here. Always you put numbers in front of a chemical equation, which we call it coefficient. And that way you balance the equation. So the best way to start is to balance or to start balancing the polyatomic ion first. And now know the different yeah. If there is any question during the line, please ask me. Okay, raise your hand so that I can able to identify you. Know the difference between acid and bases. Also identify what monoprotic, diprotic, and polyprotic acids. Monoprotic or diprotic or polyprotic. First of all, it depends of the number of counting of the hydrogen ions. You can identify they are monoprotic or diprotic or polyprotic. So like if you have one hydrogen, it's called monoprotic because of that one hydrogen. If it is diprotic, you have two hydrogen. If it is three or more than three, it's called a polyprotic acid. Okay. Now, remember that study the definition of acids. Acids, they have two definitions. One is Arrhenius definition of an acid. Okay. The second is Brown and Lemay definition of an acid. Brown and Lemay definition of an acid. Okay, these definitions are found in chapter 4. You can see them in chapter 4. The RNS definition of an acid. This one says that acid always have substances that have hydrogen ions in it, and a base or alkaline solution are substances that have OH ions in them. That's how a base should be. Okay, so that is one definition. That's RNA's definition of an acid and a base. So also the Brown and Lemay definition of an acid is a little bit different. That Brown and Lemay define acid. Acid is hydrogen donor. Okay, and the base is hydrogen acceptor. Maybe I can able to give you the explanation later on, but these definitions, find them in PowerPoint. You can look at them, what means by an acid and a base. So knowing about the solubility guideline, it also helps you to write ionic and net ionic equations. You know, so that you can able to identify the spectator ions as well. We have given some example. We did some examples. I also had an example here. We have a molecular equation, which is a lead nitrate reacts with potassium iodide. That gives you a lead iodide as solid. S refers to solid, and then you can able to see the by removing the spectator ions, you can get into a net ionic equation. So this problems is related with the solubility guideline, which we have here on the top. So also we need to know about the difference between strong acids and weak acids, name them as well. Mostly strong acids are acids of halogen families, okay? Acids of group 7. Of course, there is some exception, like hydrogen fluoride is a halogen family. It's an exception, okay? Sometimes we have to accept as an exception, but most halogen families are strong acids, as well as acids like sulfuric acid, nitric acid, as you see here, HCl, HBr, HI, HCl4, they all are strong acids. And weak acids includes like phosphoric acids, derivatives of strong acids like nitrous acid, sulfurous acid are considered as weak acids. Nitrous and sulfurous, they made from like if you have sulfate, by taking away oxygen, you'll have sulfite. This is sulfate. This is sulfite when we studied names. So the acid made from sulfate would be H2SO4. The acid made from sulfite would be H2SO3. So these are weak acids. Any derived acids are like sulfurous acid, because it's derived from a sulfate ion, it's considered as a weak acid, whereas this is a strong acid. Nitrate versus nitrite, for example. Always a deficiency of oxygen indicate that the acid composed from derivatives of oxygen is weak acid. So we have like HNO3 versus HNO2. So this is a strong acid, whereas this guy is a weak acid. So again, this is nitrate, which is ATE. This is nitrite, which ends with ITE. So acids composed from ITE groups are also considered as a weak acids. That's why we have HNO2 here and H2SO4, H2SO3 here. I'll make, maybe I can update this and send it to you later. Organic acids or carbonic acids are considered as weak acids as well. So bases, such as alkali metal bases, are considered strong bases, and by default, they are strong electrolytes as well. So strong acids are strong electrolytes, weak acids are weak electrolytes. They correspond, they affiliate each other. Strong bases are always strong electrolytes as well. So some of examples of weak bases here, bases that made from aluminum, any elements from, I would say, elements that made from uh, other elements made from alkali metals and alkaline earth metals, okay? So that they can be a weak base. Ammonia is also a weak base. Weak base, basically it means that it's a weak electrolyte, okay? Um, I was talking about here derivatives of strong acids like nitrates and sulfides. By default, they are weak electrolytes. I already gave you an example earlier. If you compare nitric acid versus nitrite acids, nitrate and nitrite. So the nitric acid, the HNO3 is a strong one, the HNO2 is a weak one. So technically, any acids made from the ATE group is a strong acids. Okay, any acids made from the IT group like HNO2 is considered as a weak acids. Okay, know the difference between oxidation and reduction reactions. We learned and discussed about oxidation and reduction. Let me just save this because later on I'm going to send this to you along with the video presentation today. Okay. Okay. Oxidation and reduction. Oxidations are always related with the loss of electrons, and reduction is always related with the gain of electrons. So traditionally, we can say that metals are oxidized in a process that metals always are related with the process of losing electrons, whereas non-metals are reduced, which means non-metals are gaining electrons. Uh, However, like there are situations, here is a good example that explains that. Consider a solution of copper 2 chloride and calcium metal. Calcium and copper, both of them are metals. So, but copper is above, calcium is above copper in the activity series of metals. So in this case, we also need to identify which of the two metals will be oxidized and which of the element is reduced. So in order to answer that question, I have a list of the activity series of metals in aqueous solution. So this series would be helping you for the question that was asked here in the on the top, which is by comparing the reaction of copper chloride and calcium metal, you have to always look on the activity series of metal. As you see here, calcium is found here, whereas copper is found here below. So any element above is easily be oxidized. Any element below is resisting to oxidize. So if there is a reaction between calcium and copper chloride, there's going to be a reaction because calcium is above copper, which is more reactive. It can easily be oxidized. Then it's going to be calcium chloride and copper. So in that case, calcium is oxidized and copper is reduced. Okay, this is because of the location where copper, those elements in the bottom are resisting to oxidize. Resisting to oxidize. Elements in the top easily be oxidized. They are very active. They can easily be consumed, easily be oxidized, easily be losing electrons. So they can be oxidized. They are not easily be oxidized. They are not easily be losing electrons. So So they tend to reduction process. So that is also with the metals to metals. Basically, oxidation and reduction reaction is between metals and non-metals. There is no problem. If it is within metals and non-metals, you can easily answer the question. But if you have a reaction between like this, calcium with copper chloride, then you have to study or you have to explore the list of the activity series of metals in aqueous solution. That might give us some tip. And then the next thing that we discuss is, you guys hearing me, right? You guys hearing me well?
Yes.
Okay, okay. If there is any question, if I'm any question, please let me know. Okay. I want to make sure that whatever I'm writing, you hear it. I mean, you take note, and also like you hear me very well. Know how to calculate oxidation number from a given compound. So oxidation number is something that discussed in chapter 4 also. What is oxidation number of phosphorus in sodium phosphate? So oxidation number is not necessarily mean the charge of the ion. So, but the basic concept for oxidation number is when you have a compound like sodium phosphate, their oxidation number would be 0 because it's a compound. For a monoatomic ion, for example, we have sodium, we have a +1, phosphorus, we have a -2. If we are looking for the oxidation number of phosphorus, so that's going to be 3 plus X to get the oxidation number of phosphorus, -8 would be 0, X minus 5 would be 0. So by adding 5 from both sides, so we can calculate the oxidation number of phosphorus, which is 5. Okay, oxidation number doesn't necessarily mean the charge of the ion. So look for the slide that explain about oxidation number. It's in chapter 4 again. For polyatomic ions, for instance, I have nitrate ion. Nitrate has the entire charge of -1. So when I work with a nitrate ion, if I want to find the oxidation number of nitrogen in nitrate, which is, I would put X. The oxidation number of oxygen is always -2. And I have 3 atoms of oxygen. 3 times -2 would be -6. It's altogether it would be -1, not 0. 0 is always if you have a compound like hydrochloric acid, their entire oxidation number, the sum of oxidation number, considered as 0. But for a polyatomic ion, the oxidation number is the charge of the ion. So when we add X plus -6, which is -1, so to get X, which is oxidation number of nitrogen, we add 6 on both sides. So that gives us a +5. That's the oxidation number of nitrate. Nitrate and the oxidation number of nitrogen in nitrate. So oxidation number will also be a part of the problem. Here is an example. Maybe you can make a practice. Identify which elements oxidized and which elements reduced, as well as the number of electrons which are reduced or oxidized. While you are doing the review guideline, and in case that you have questions that you not easily answer, you can text me or send me a text message with your name. Use this number, text me for a quick answer. Then I'll reply to you, and then we can able to work from there. Okay. Now, how do we measure the strength of an acid? The strength of an acid and a base would be another question. The strength of an acid and a base, one of the measurements we use is a pH value. The pH value runs between 1 and 14. That's the range of the pH value, which we have like 1, 2, 3. These are considered as strong acids. If the pH value of 1, 2, 3 will be strong acids, around 6 and 7 considered as a neutral, 8 and 9 considered as a weak base. Something like 11, 12, 13 is considered as strong base and weak acids as well. So the pH number, pH is actually measured as minus log of the concentration of hydrogen ion. This is one of the measurements of pH. The other measurement for a pH is a litmus paper. A litmus paper, if you have any questions, please raise your hand. A litmus paper, if Foma, I think you texted something, but I couldn't able to read. Okay, Abimola, go ahead, Abimola, please.
Yeah, I just want to confirm. I hope we're not going to get any questions about calculating pH using the minus log thing.
No.
No, okay.
No, I'm not going to. I'm just asking. Maybe I will have to ask you a question. Focus of what we discussed, Abimola. That's a good question, by the way, because I didn't do any practice questions on that. Doing the calculation, I don't think it's necessary for us to do that. But at least I can able to ask you if you have a pH value of 1 or 2, what do you think the acid would be? Is it a strong acid or a weak acid? So you can answer that, I'm pretty much sure, right, Abimola?
Yes.
Or if it's 11 or 12 or 13, what would be the status of substance? Is it a strong base or a weak base? I don't think something like this wouldn't be a problem.
No, it won't.
Litmus paper. Litmus paper is also another measurement. Litmus paper indicates red in acidic solution. It turns into blue in a basic solution. That's also another thing that we have to know. We have to identify. Also, I'll just acid rain versus a pure rain. Okay. Acid rain versus a pure rain. Acid rains made from it's also in chapter 4, made from nitrate and sulfate. Okay, and then you will have also the pure water rain that's made from a pure water rain made from carbon dioxide. Made from carbon dioxide, react with water, we get carbonic acid. Acid rains made from nitrate and sulfate, they will give you nitric acid and sulfuric acid. Okay, this is something we discussed or we covered on the lecture. Let me just save this. I will, for the reference, I will give you this as, oh my gosh. Let me see here. Okay, I'll later on update it, send this to you anyways. Well, study the formula of a unit of molarity, a mole of a solid per liter of solution, calculating about molarity. We have been discussed about molarity, so I'm not going to spend a lot of time in molarity, but I would like to invest some time with the chapter 5. I think I'm not going to challenge you with all the questions in chapter 5. However, there are certain points that we need to know in chapter 5, like what's the kinetic energy, which is a formula of kinetic energy is 1/2 mv squared. Also, we need to learn about units of kinetic energy. The units of kinetic energy is joules, which is J, big J. It's the SI unit. Of course, there are other units like calories. 1 calorie calorie is considered as a metric unit. Calorie is equals to 4.184 joules. There is a big C calorie to a big C. There's a difference between big C and small c. Actually, I have posted chapter 5, a modified version of chapter 5 in a module section. I don't know how many of you have seen that. Did you see that, the modules? And then I also indicated the slides, the specific slide number. I wrote it for you. I'm sure that you received that announcement. Abimola, did you guys see that? There is a specific slide that I pick from chapter 5 that I want you to read. That will help you to prepare. Anybody, did you see that?
Yeah, I saw it.
Okay, okay. So the number of slides, and basically the number of slides, and the PowerPoint is also there. If you see it, I think pretty much everyone will you received it then. Also, we have to know what is the let me just make this one here. Oh, to make it exponents, yeah. Okay. The joule, 1 joule is, I'm just using kinetic energy formula, which is 1/2 times m times v squared. So 1/2, if you assume that the mass of the object will be 2 kilogram, would have a speed of 1 meter per second, that's a joule will be calculated. So 1 joule basically equals to 2 and 2 will be crossed out here. As you see, there will be these 2 and 2 will be crossed out. So 1 joule would be 1 kilogram meter square per second squared. That's equals to 1 joule. So this is also important term to identify what's 1 joule equals to. Okay.
Excuse me, Professor.
Yes.
Unless if I don't see correct, it said 1 calorie equal 1,000 calorie. Is that correct?
Yes, yes. The 1 big calorie, there's a difference. Actually, the big C refers to nutritional values. So 1 big C calorie equals to 1,000 calorie, which is equivalent to 1 kilocalorie, by the way. Okay. So yeah, yeah. One big calorie equals to 1,000 calorie. That's also, I will put equal sign here, which is 1 kilocalorie. If you want to change 1,000, you can take 1 kilocalorie. Okay. Does that make sense, Abimon? I mean, Kalala?
Yes.
Okay. So another thing that's also, which I would like to discuss with you, is that how do we calculate heat loss or heat gain by substance? This is something that is, oh boy. The heat transfer or the heat loss or the heat gained is calculated as Q equals to M times C times delta T. What it means that, for example, what type of questions are we going to discuss? Okay, let me save this. Let me go back with the PowerPoint so that that might be easier to write. Let me save this for a quick. Okay, so sure the chapter 5 would be here, a modified chapter 5. The final exam is next week, IFOMA. So it's going to be next week, next Tuesday. IFOMA, do you hear me? I just saw your text now.
Yes, Professor.
Okay. Let me, This PowerPoint is actually, you can find this PowerPoint in the module section. So number 40, like the kinetic energy is the energy of motion, which I mentioned the formula is half times mv square. Potential energy is the energy of an object possessed by its virtue of its position. Here is also the units that I was discussing. The units for kinetic energy is SI unit is joules, and 1 calorie equals 4.184 joules, and 1 big calorie, which is 1,000 calorie, equals to 1 kilocalorie, the ones that I discussed earlier. Another important thing that we need to know is systems and surrounding. If you remember from chapter 2, we were discussing about the law of conservation of mass. The law of conservation of mass, if you remember that, we stated that, for example, if you have, okay, this is not a good, maybe let me use this one. If you have hydrogen reacts with oxygen, gives you H2O, you can balance this. So if you have, let's say, 20 grams of hydrogen reacted with 15 grams of oxygen with the amount, then, you know, a new chemical substance is formed. This is like a chemical change. Okay, it's not a physical change. Now what's happening, what's interesting is that whatever amount that you started with, you'll get the same amount at the end. So that is called, matter is neither created nor destroyed, which leads us the law of conservation of mass. That leads us the law of conservation of mass. The amounts that you started with, you will get the same amount at the end. That's the law of conservation of mass. We will have the same principle, which is called energy is conserved. Here, energy is conserved, or it's the same principle as the law of conservation of energy. The law of conservation of energy. Basically, the law of conservation of energy is occurred between a system and the surrounding. What is a system? So we have a reaction inside a beaker. For example, you have a reaction here. Let's say that you have a reaction between acid and base. Hydrochloric acid react with sodium hydroxide, and it gives you sodium chloride plus water. Okay, there's a reaction here. So this reaction will generate some kind of energy, some kind of heat. So whatever reaction happens inside the beaker, it's called a system. So surrounding is what is in outside. Okay, this is called surrounding. So there's going to be a conversion, I mean a transformation of energy from system to surrounding, or vice versa. From system to surrounding, or from surrounding to system. Okay, if there is any reaction inside a test tube or inside a beaker, like a reaction between hydrochloric acid and sodium hydroxide, that's what is happening inside the beaker, that's called system. But the results, they might produce gases like carbon dioxide or some kind of gases. They might generate heat. They might produce some heat. So we can, like, if I touch the test tube here on this area, for example, I feel warm because my hand is feeling warm. Where does that temperature comes? Where does that energy actually comes from? That comes from the system. So there is always a transformation of energy between system and surrounding. So let's say that if the system is losing about 10 joules of energy. Surrounding gains the same amount of energy. Whatever energy lost by the system, surrounding gains the same amount of energy. That's the reason that we say this energy is conserved, or the first law of thermodynamics, that the law of conservation of energy would happen between system and surrounding. It's like system would be like reactant, surrounding will be a product, or vice versa. Just like you have the law of conservation of mass, we have the law of conservation of energy. So, so system and surrounding can be anything. I mean, it's between between what's happening inside the beaker and outside. That's called system and surrounding. I can give you more examples of this, what system and surrounding. Okay, we don't need this that much. This is the first, here, this is slide number 47. I mentioned about the slide number so that you can able to focus or concentrate. So how do you relate delta E? That means delta E refers as the internal energy of the system. This delta E is the internal energy of the system. Okay, so internal energy of the system first of all, like I say, energy cannot be created or destroyed. Energy of the system and surrounding is always constant, which means that any energy transferred from a system must be transferred or must be received by the surroundings, or vice versa. So that will lead us the first law of thermodynamics here, which states that when a system undergoes a physical or chemical change, the change in internal energy, which is delta E, is given by the heat added to or absorbed by the system. The heat added to the system or absorbed by the system, plus the work done on the system or the work done by the system. This is a little bit crazy here. The work done on the system and the work done by the system. The link here, it has a big significance here in terms of calculating the quantitative value of internal energy of the system. The work done on the system and the work done by the system. So work done by the system, in that case, the work refers as W. System is losing, so it's going to be like minus W, work done by the system. Work done on the system, that means system is gaining, so it's going to be plus W, okay? So on the system and by the system, we'd have a significance value here. Maybe the next slide, slide number 47, would clarify that for you. You see, like this is system here with the gray color, surrounding it here. So the system delta E, which is delta E, is Q plus W. Abimola, go ahead, please.
Yes, I wanted to know, are we going to be required to do calculations on this, or are we just to know the notations, like with minus W or plus W?
Maybe like there might be easy and straight and forward questions that will help you to understand. That was the thing. I'm going to give you an example later with this.
Oh, okay.
So
That's what I was going to say.
No, yeah, I am. Thank you for raising that question, by the way, because I have given this question, the same question, to the other class. Regardless, that would be more explainable to understand what is work done on the system or work done by the system. For example, surroundings. heat, the system gets heat from the surrounding, so the value of Q is greater than 0. System is larger here. Again, work, surrounding does work on the system, okay? So the work value will be greater than 0, which means the value of delta E is going to be greater than 0. System is gaining, surrounding is losing in this chart here. Like, for example, this might be slide number 48, will clearly explain things here about the sign convention for W and Q. When is the value of Q is greater than 0? When the value of Q is greater than 0, when heat is transferred from the surrounding to the system. Okay, when is the value of Q is less than 0, this is Q means that's Q refers to heat. Okay, so internal energy of the system, that is here, which is delta E, which is Q plus W. When is Q less than 0, that means heat is transferred from the system to the surroundings. So heat is transferred from the system. The system is losing heat, surrounding is gaining. Now the sign convention for the work would be greater than 0 or would have a positive value when work is done by the surrounding. I always see that many of you get confused with the word by the surrounding on the system. Who does work? The surrounding does work on the system. So surrounding provides work to the system, so the value of work will be greater than 0. Over here, the value of work would be negative, which will be less than 0, because work is done by the system on the surroundings. So the preposition by and on would be is a significant part. If work is done by the system, the value of W would be less than 0 because system is losing energy, whereas surrounding gaining energy. Okay, so to make these ideas clear about the transformation of energy and work between system and surrounding, so there are two things that you need to know. First of all, the law of conservation of energy. If whatever energy is lost by the system is gaining by the surrounding or vice versa. That's important. There is always convergence between work and there's always conversion of transformation of energy between work and surroundings. That is the first law of energy, the first law of thermodynamics, like energy is conserved. The second thing is that when is the delta E value greater than 0, the internal energy of the system, when is the delta E value is less than 0? That's another thing that we have to also take into consideration. So it might be a good idea, like what Abimola asking me earlier, to understand this sign convention. If I give you a quantitative example, so like I picked one good example for my other class this morning. I'm going to give you that example at the same time, which is okay, got it. Okay, please write this note, this question, and we can solve this together. This would be a good example to explain the ideas that I was talking about. Okay. Practice example related to internal energy of the system. That means which is delta E. So the question would be like, calculate the change in the internal energy, the change in the internal energy for a process in which a system absorbs 140 joules of heat from the surroundings, okay? From the surroundings. And does 85 joules of work, 85 joules of work on the surroundings, okay? So let's explore this question. Here, so we have a system here inside. We have a surrounding here outside. This is surrounding. So there's a transformation of energy between system and surrounding, and we know that the transformation of the system and transformation of energy between system and surrounding is constant. That's the law of conservation of energy. Now let's read the problem. You need to calculate the change in internal energy. The change in internal energy, they are talking about the delta E. Delta E is going to be Q plus W, which is Q refers to as heat and W refers as work. All right. So calculate the change in the internal energy for a process in which a system absorbs 140 of joules of heat from surrounding. So 140 joules of energy system absorbs. So Q in this case will be positive or negative?
Positive.
Positive, because we're dealing with internal energy of the system. This is right here, right? System gains, absorbs. Absorbs means it gets to its account. That's internal energy of the system. So delta Q, the value of Q is positive, which is 140 joules, right? Now, but we're not stopping there. The system absorbs this much energy, 140 joules of heat from the surrounding, and the system does 85 joules of work on the surrounding. What does that mean? The system does 85 joules of work on the surrounding. So system is releasing or giving 85 of joules energy. So does system gains or does system gains or lose work here?
It loses.
It loses, so it's going to be negative. It's going to be minus. It's lost. So the way the internal energy of the system would be what? The internal energy of the system would be plus 140 joules minus 85 joules. You see? So that's how the understanding comes. So it's going to be, what would be, the question would be, what would be the internal energy of the system? That's going to be minus 85 plus 140. I'm sure you have a calculator with you. You can help me on that.
50.
It is about
55.
55 plus 55. This is the remaining internal energy of the system. It absorbs 140, however, it provides, or it does work with the value of 85 joules of work to the system, to the surrounding, I'm sorry. This is how system and surrounding can be explained. So you can integrate this example with the slides that I mentioned earlier. with the convention of the slides that I mentioned earlier, okay? I'm going to send you anyway the video of this record so that you can have this explanation. Like I say, if you have questions, you can also text me on the number here so that we can able to discuss, okay? So the next thing is about the let me go back to the review guideline. Okay, so okay, explain the system. Okay, let me go back with the review guideline. There is how do we measure the heat loss or the heat gain? Okay, no, wait a minute. Let me before that. Yeah, there's also another thing that we need to discuss here. It's better I can able to write more perfectly on a PowerPoint. So, do you see the PowerPoint now?
Yes.
Do you see the blue PowerPoint, Abimola?
Yes.
Okay.
But nothing
Okay.
written on it.
Okay. No. Okay. Yeah. Yes. I know. Let me. How about now? Heat lost.
Yes, we can see it.
Okay. Or heat gained by substance can be measured as Q equals to mass times specific heat times change in temperature. Which is M times C times delta T. All right. So this is also how do we, okay, we said that system lost 55 joules of energy, surrounding gains 55 of energy. How do we measure energy? How do we measure the transformation of energy? Okay, so this is a formula that we're going to use, mass times C times delta T. So specific heat, which is C, which is called specific heat, that means, it means that the amount of heat which is required to raise the temperature of 1 gram of a substance by 1 degree centigrade. That's what specific heat means. The amount of heat required to raise the temperature of 1 gram of substance by 1 degree centigrade. So specific heat value would be constant for different substances. We use the specific heat of water, for example. The specific heat of water will be given to you. It's 4.18 joules gram per degree centigrade. What it means that to raise the temperature of 1 gram of water by 1 degree centigrade, you need to have about 4.18 joules of energy. This one has a lot of significance, a lot of metabolism, a lot of significance in our daily life. Sometimes, you know, biologically, our body is composed of 75% of our body is water, you know, it's composed of water composition, if you think about it. In summertime, like we are like sweating, but our internal body temperature is always kept constant. It's because of the specific heat of specific heat capacity of water. Will be dehydrated if it is over 400, if it is over 100 degrees centigrade. We're dehydrating from the outside, not from the inside. Or we can also see the practical example, like if you go to an ocean city, summertime, in the beach and the places like that, you always see that the sun is very, very hot. It burns your feet, whereas the water is always cold. It's one of the reason, actually, what's the reason behind it? The reason behind it is that the specific heat capacity. The specific heat capacity for sun is much lower. It absorbs much energy to raise the temperature. They both get the same amount of energy from the solar system, from the sun, but the water still remains cold, but the sun is burning your feet. So that's also one of the explanation with the specific heat capacity value. So now the question is, how do we measure specific heat of a substance? So a numerical example, I can also give you a numerical example related with that. Um, I'm sure that you take a note on this. Have you taken a note on this? If you do not take a note, that's fine, because it's also be recorded and it will be sent to you. So I may have to remove it at some point. This is also included in the review guideline anyway. It's posted there. So, but let me give you a practical example that is related with the calculation of heat lost or heat gained by a substance. So maybe like we can, I can give you, um, hmm. Okay, here's an example. How much heat is needed to warm a 250 grams of water from 22 degrees centigrade, which is about room temperature, to 98 degrees centigrade. Okay, so how much heat is required? The amount of heat. And the specific heat capacity for water would be given to you. Is 4.18, I think 4 joules per gram degree centigrade. So in that case, to do the calculation, you have a water initially has 22 degrees centigrade. You wanted to bring the water into another set of temperature, which is 98 degrees centigrade, from 20 to 98. So how much heat is needed? So you are asking the amount of heat that's needed to raise the temperature from 22 degrees centigrade to 98 degrees centigrade, you see? So in that regard, we have our formula, which is Q. I use Q. The Q can be heat lost or heat gain. It's going to be mass times specific heat times change in temperature. So the mass would be 250 grams. Specific heat of water would be 4.18 joules per gram degree centigrade. The change in temperature, which is delta T, is going to be T final minus T initial. That's going to be 98 degrees centigrade minus 22 degrees centigrade, which I believe it gives you 76 degrees centigrade. So we multiply this. So if you multiply, someone can help me just to get correlation. 250 times 4.18 times 76. So what do you get? 250 times, okay, hold on. 250 times 4.18 times 76. I don't know, you can check with me, please. 79,670 joules of energy is needed to bring the temperature of 22 degrees centigrade to 98. Am I right? Can I have a witness, please? 79,670 joules.
What about significant figures?
We can, yeah, we can, yeah, yes, we can write this as a scientific notation. So 250 would be three significant figure. I would go with 7.97 times 10 to the power of 4 joules.
So I got a
Right.
different number. This is
Okay.
Miriam.
Okay.
I got,
okay.
when I multiplied it 250 times 418 times 76, I got 79,420.
Yeah, that's what I'm asking you. If I get 250 times 4.18
times 76.
Is that Suzanne? Who is that? Is that Suzanne?
Miriam. No, it's Miriam.
Miriam. Okay. 250 times 4.18 times 7. I got 7. Okay, you're right. 79,420. Yes. Yes.
Yeah, and then I just had a question about the unit. So you cross off the grams cancels out, and the degrees Celsius cancels out, and you're left with
okay.
joules.
Yes, definitely. Give me a second. Yes, Miriam, that's going to be 79,420 joules. Yes. Now here, grams and grams will be cancelled out. Celsius and Celsius will be cancelled out, and joules will be left. Okay. Now,
Okay.
we also have to learn to change this into a kilojoules, Abimola. So, 1 kilojoules equals to 1,000 joules. Okay, kilo refers to 1,000. So it's a common practice that mostly energies have it's the big values, so they have to be converted into kilojoules. So 79,420 joules converted into kilojoules. That gives me 79.420 kilojoules. Can you guys verify that? And then significant figure is going to be 79.4 kilojoules. You agree with me?
What about it too?
I just rounded up to three significant figures just to
Random, yeah.
right. I don't know where was that. The amount was okay because of this, because of the mass. Does that make sense?
Yeah.
Okay. All right. Okay. Is this about the calculation of heat gain or heat loss by substance? Okay. Hold on, let me go back here. Good. Now we can able to go back to our review. The review paper that I gave you, which is okay, give me a second. Which one? The one that's updated, that's what I would like to work with. Okay, so let's see. I'm able to share it now. I think this one is here. This is the one that's updated, I guess. Yeah, we're here. Okay. So heat lost or heat gained, I was tapping here. Did you see the review guideline now? So that was the one that I discussed with you earlier. Okay. And now let's go on that. Come on. So know how to calculate the molar concentration and relative concentrations of a compound. So we discussed about molar concentration, like molarity, but I don't think we discussed about the relative concentration. So I'm going to explain a little bit about what relative concentration means. So here is an example. What are relative concentration of calcium ion and acetate ion afforded by dissolving 0.700 moles of calcium acetate in water diluting to 135 milliliter. 1 liter equals 1000 milliliter. So in a situation like that, first calculate the molarity of the entire solution. When they say the entire solution, they are talking about the molarity of calcium acetate, which is this guy here, calcium acetate in water. Relative concentration. Okay, relative concentration is indicating that the concentration of individual ions. Okay, let me just write that down for you so that you'll get a clear understanding. When I say relative concentration is the concentration of individual ions. Okay, so in this case, so if you have equations, everybody knows how to calculate molarity. I'm certain on that, but it's just a little bit different here, the different setup here. When they say relative concentration of, they wanted to know what's the relative concentration of calcium and acetate in a compound afforded by 0.700 moles of calcium acetate. So I would calculate the molarity first, the molarity of calcium acetate as it is. Okay, so the molarity, we discussed about molarity is always N over V, the number of moles divided by the volume of solution. For the sake of convenience, we have given the number of moles, which is 0.700 moles. And the volume is about 135 milliliter, but however, 135 milliliter has to be changed into liter. It gives you 0.135 liter. So when you divide these values, you will get that 0.700 divided by 0.135. That gives us 5.18 molarity. Now remember, this is for the entire solution for calcium acetate. This is for the entire solution. Now, the relative concentration for calcium and the relative concentration of acetate, depending on the decomposition or the ratio of the compound in calcium acetate. Calcium acetate, when it's decomposed, you have like 1 calcium ion and 2 of the acetate ion. So 1 mole of calcium acetate generates 1 mole of calcium ion, 2 moles of acetate ion. So the ratio is like 1 to 2. So if you have 5.18 molarity of calcium acetate, the relative concentration of calcium would be 5.18 molarity. The acetate ion would be 2 times 5.18. So in this case, the relative concentration of calcium acetate would be about what? About 5.18 times 2.
10.36.
10 point?
36.
10.36, yes. It's going to be 10.36. And this guy will be 5.18 molarity. Okay, that's how relative concentration is calculated. Relative concentration is focusing on the individual ions, whereas the others one are the relative. When I ask you the relative, I mean when I ask you the concentration, it means that the concentration of the entire compound. Abimola, please. I'm sorry, Abimola, go ahead.
Yes, I was going to ask why why is the concentration of the constituents of the whole of the solution, why is the total more than the concentration of the entire solution? Like the calcium is 5.18 molar, and the acetate is 10.349 molar.
About 10.36.
Yeah, about 10.36.
Yeah.
Okay. Okay. So why is that more than the concentration of the entire solution?
Okay, you have to see in a point that let's say that we're talking about the concentration of the individual ions. Say, for example, if you have calcium carbonate, right? When calcium carbonate decomposed, you'll get equal ratio of calcium oxide and carbon dioxide gas. Like, let's say if you have 1 mole of calcium carbonate, gives you 1 mole of calcium oxide and 1 mole of carbon dioxide, right?
Yes.
Because the ratio is 1 to 1. If it is 2 mole of calcium carbonate, it gives you 2 moles of calcium oxide and 2 moles of carbon dioxide. Okay, look on the situation that how much ions they generate or how much ions they produce. Let me put it in you know, when you everybody drives a car, so you know the safety balloon that you have in your car is a gas. I think it's a sodium azide gas. Okay, it's very few amount. It's like that is like maybe like 1 gram. Okay, when collision happens, it automatically creates a decomposition reaction. A decomposition reaction would create a huge amount of nitrogen gas. A huge amount of nitrogen gas would fill the balloons, and that helps you to protect you, nothing to happen to you. But when you consider about the amount that you have that is kept in your car, right, is 1 gram, but the amount of nitrogen gas may be more than that. That's how it generates. It produces a bigger amount. That's why the balloon comes out and it covers your chest. It covers you generally. But remember, in your car right now, if you have a measurement, how much sodium azide that you have, it's called sodium azide. It's very little, maybe 1.5 grams or 2 grams. But the amount of nitrogen gas that's generated will be more than that. That covers you as, you know, nothing will happen to you. So we're not balancing the equation here, Abimola. We're not balancing the equation. We are looking at 1 mole of calcium acetate will generate 1 mole of calcium ion and 2 moles of acetate ion.
Okay.
That's how the ratio is. Now, but we have 5.18 molar, right? So that 5.18 molar directly goes to, for calcium, the same amount. Unfortunately, not for the calcium acetate because it generates twice of that. It doubles that. So every 1 mole can produce 10.38 moles. That is how relative concentration is about. If you see it, it looks like no, that doesn't seem right. But the relative concentration and the entire concentrations are different. The entire concentration might be smaller, but the amount that they generate, the amount that they developed, maybe more than they have at the beginning. Sodium azide is a good example. It's just a salt. It's a salt. Sodium azide is a salt. It's kept in the stirring. So if there is a crash or if there is an accident happen, automatically when another car hits you, then it explodes. It explodes and the balloon comes out. The balloon comes out from the nitrogen gas from here. That's a huge amount from 1 gram, from the smaller amount. Does that make sense, Bimola?
Yes, it does.
Okay.
Thank you.
Thank you, sir. Okay, so let me go back. So the other thing that we need to know how to calculate a diluted solution from concentrated solution. Again, I would invite you to go to Luke chapter 4. We are discussing and we spend huge amount of time stock solution versus diluted solution. The way how we dilute solution is by adding water. So examples were given. I'm very much certain on that. So review those pointers, how to calculate. The key formula there is MCVC equals MDVD. That's the key part there. MCVC equals MDVD would be very, very helpful. So I have an example here. Do the examples. If you really have questions, I would be happy to answer your questions. But we have done this example. Okay, this example was covered in the lectures last week or a week ago, I guess. But here is also an example, so you can practice that. So here we also need to know about titration. What's titration? Findings, what is titration, what's end point, what's equivalent point, okay? I gave you the definition of titration. Titration means finding the concentration of the unknown solution by using a standard solution. This is also helpful for your lab class. We also discussed that in a lecture class. So titration means that finding concentration of unknown solution by using a standard solution. So for example, I know many of you are not in my lab class, but let's say that if you have 2 molarity of sodium hydroxide and X molarity of hydrochloric acid, okay? This is called a standard solution. The reason why I say standard solution, because its concentration is known. Okay. Now, X hydrochloric acid, this one has unknown concentration. So the whole idea of titration means that by using a standard solution here, which is 2 molarity of sodium hydroxide, you need to determine the unknown concentration of hydrochloric acid. That the whole point is called titration. And its definition is right here. Finding the concentration of the unknown solution by using a standard solution. And standard solution means that it's a solution whose concentration is known. Once you know the concentration, once the concentration is given to you, then that's called a standard solution. Then we have equivalence point, or sometimes end point. Okay. There is a slight difference between equivalence point and end point. I'm going to explain that. Theoretically, they're the same. Practically, they are not the same. End point is actually a practical word. Equivalence point is a theoretical word. Equivalence point means that theoretically, if you have the number of moles of an acid equals to the number of moles of a base, okay, that's called equivalence point. When you do titration, you have to look something called equivalence point, which means the number of moles of an acid equals the number of moles of a base. I use Na. Na refers to moles of an acid, and Nb refers to moles of a base. That's called equivalence point. Okay, so yeah. So what we are talking about here that, but how do we know? How do we know we get into equivalence point? We use an indicator called phenolphthalein. Phenolphthalein is an indicator. When we get to that point, the color changes into a light pink color or a faint pink color. Okay, that's what we call it the end point actually. Okay, the way how we know this is actually, here is an explanation. By using an indicator, the indicator is used, phenolphthalein is it's a color media. It's colorless in acidic solution. It's also pink color in a basic solution. It's written here. And you may see a faint pink color, light pink color. That means if you see a light pink color, that means that's end point. You stop the reaction, which means the light pink means that theoretically you get into equivalence point. So that means you get into the number of moles of an acid equals to the number of moles of a base. But the light pink shows you that stop. That's where you stop the reaction. Okay, so that's how end point means. So you will also have to get these ideas. What is equivalence point? What's the standard solution? What's the titration? And what's end point means. Also that how is the formation of acid rain versus pure rainwater? Also, I was explaining about that. Acid rain is basically forming from mostly from sulfur dioxide and nitrogen dioxide. If it is a polluted or contaminated area, when they react with water, they provide nitric acid and sulfuric acid. So a pure rain is formed from when carbon dioxide reacts with water, with carbonic acid, for example. Okay, so this is called a pure rain. That's a natural rain, we can say that. Here, okay, I'm glad that I mentioned this point again. Know the definition of Brown and Lemay concept of acid and base. Here is an example given to you. Let me make a little bit correction here. Okay, so the RNS definition, earlier I wrote a note when we started. RNS definition is basically, it is like a substance that has hydrogen ion is considered as acidic. A substance that has OH ion is considered as a basic. This is a straight and forward definition, and we listed many examples like hydrochloric acid, nitric acid, perchloric acid. All these are acids due to the fact that they have hydrogen ion. Something like sodium hydroxide or calcium hydroxide, something like ammonium hydroxide, they are bases because they all have OH ions. This is called the RNS definition of acid and base. You also have to learn that the fact that there is another type of definition which is called I'm on Zoom right now. I'm online. Hello, can I call you later because I'm on Zoom right now. I'm with my students. Okay, that's fine. Okay, sure. Okay, so okay, so but the Brown is the Brown and Lemay concept of acid and the base. That's going to be Brown and Lemay concept of acid and base is different. So that is here is an example is given to you. Sulfuric acid reacts with water, gives you H3O plus HSO4 minus 1. In this example, sulfuric acid is an acid, according to Brown and Lemma, because since it has a hydrogen or a proton acceptor. No. Sorry, a proton donor should be donor. It's not acceptor. I don't know why I said that. Sulfuric acid. If you look sulfuric acid here, sulfuric acid gives hydrogen ion to water, and it becomes H3O here, and it loses hydrogen here, right? So in this case, sulfuric acid is an acid because it's a proton donor or a hydrogen donor. All right. I'll give you this later on anyway, so that I can update that for you. Water, in this case, is considered as a base. Be careful. Water, in this case, is considered as a base. Okay. Why? According to Bronsted-Lowry definition, water is a base because it accepts hydrogen ion from sulfuric acid. It becomes H3O. It accepts hydrogen and turns into H3O, okay? And on the other hand, now when we look from the product side, every acid have a conjugate base. Every base has a conjugate acid. So since sulfuric acid is an acid, HSO4 is a conjugate base. Abimola, give me a second. Maybe I may answer your question, okay?
Okay.
And then HSO4 is considered as a conjugate base from H2SO4. Every acid has a conjugate base. I can give you one example later with that. Go ahead, Abimola.
Yeah, my question is that Brown and Lemay or Bronsted-Lowry definition of the acid?
Bronsted-Lowry, yes.
Because it says on there Brown and Lemay or Brown-Lemay.
I need coffee, sir. Bronsted-Lowry, yes. Bronsted-Lowry, yeah. Concept of an acid. Thank you, Bronsted-Lowry. You're right. It's on chapter 4, right?
Yes, sir.
Okay, thank you. Thank you for the correction. Okay, so that's Bronsted-Lowry. Yeah, let me, you know what? Let me save this so that I can upload that for you later on. Give me a second. This has to be saved first. Okay. Uh-oh. What happened? I can not able to write. Oh, okay. Okay, so yes, okay. So okay, for example, let's see here. Let's say that I have NH3 react with water, gives you NH4 plus and OH minus, all right? Here is my question for you. We can do this together to save time. Which one is an acid, which one is a base in this reaction? According to Bronsted-Lowry concept of acid and base. Which one is an acid, which one is a base, which one is a conjugate acid, and identify the acid and the base and the corresponding conjugate acid and bases. Okay, so who can answer these questions, please? Is NH3 an acid or a base? Abimola, please go ahead.
In this case, NH3 is the is accepting the hydrogen from the product, so it's the base, and then the H2O is the acid in this case. So
I agree.
water becomes the conjugate base in the reactant side, I mean the product side, and then the NH3 becomes, with the NH4 now, will be the conjugate acid.
Yes, because NH3 the base, it's conjugate acid. So it's going to be conjugate acid here. And the OH would be what?
That is the ammonia, which is the base, will become the conjugate acid on the other side as NH4 plus.
Right. So the OH minus would be?
Will be the conjugate base now.
Yes. Yes. That's how Bronsted-Lowry definitions of acid and bases. Good. So this is also covered in chapter 4 as well. There are two definitions. The first one is RNS definition. Second one is a Bronsted-Lowry definition. Okay. Know what strong base, strong acids, we discussed about that. Know the difference between endothermic and exothermic reactions. We discussed about when we discussed about system and surrounding. It's like a repeating units of it, joules in SI system, calories. I discussed about that earlier. Units of specific heat capacity, joules per gram degree centigrade, or joule per gram degree Kelvin. In this case, don't be confused. 1 Kelvin equals 1 degree centigrade. It's like a ratio here. Okay, so they use either joules per gram degree centigrade or joules per gram degree Kelvin. It's a ratio, so it doesn't make any difference here. In case if you see a question like this, don't get confused. 1 degree centigrade equals 1 Kelvin. Take it that way here. We take the proportion value. Okay, we're not going to discuss Hess laws. I'm going to remove that. But we have to do some calculation with the kinetic energy here. Here, for example, calculate the kinetic energy in joules of automobile weighing 157 pound, 157 pound, and traveling 80 miles per hour. Convergence, okay, the convergence factor basically will be given to you. One mile equals 1.6093 kilometer, 1 pound is 453.5 grams, 1 kilogram is 1,000 grams, 1 hour is 3,600 seconds. Okay, every conversion will be given to you. Okay, I don't know why all these are given to us. Okay, but it's okay. I mean, I don't want you to confuse with the conversions. You don't have to memorize conversions. So the kinetic energy, the idea of calculating kinetic energy calculated as 1/2 mv squared. So the mass would be given as, remember, the unit for kinetic energy is joules, right? Joules is SI system. I know now where the mistake is, because it is given, the mass was given in 157 pound. Pound is not the the SI system, it's a US system. So the pound has to be changed into kilogram. Okay, so that's the reason, because the unit of mass is in kilogram, and also, okay, traveling at a speed 80 miles per hour. Mile per hour has to be changed into meter per second. Okay, so that's the reason that we have all these conversions. So you have to change 80 miles to meter, okay? The fact that 1 mile equals 1.6093 kilometer, okay? hour, 1 hour is 3,600 seconds. That has to be changed as well. So that's how the conversion works here. So, so that the kinetic energy value will be 1/2 mv squared. The 157 pound has to be changed into kilogram, which means that the value of okay, what I'm going to do is that the 157 pound has to be changed into grams first, and the gram has to be changed into kilogram. That's how the conversion works here. So 157 pound times 1 pound equals 453.5 grams. I would say 454 grams, okay? Pound and pound. I need your help in calculation. And then once this is changed, then we're going to change the grams into kilogram, which means that 1 kilogram over 1,000 grams. All right, so this would be, this gives you about 157, let me see. $157 times 454, okay, 71,278, that's divided by 1,000. I have 71.3 kilogram. Okay, do you agree with me? Please raise your hand or say yes. That's what my calculator, my cell phone calculator tells me. But let's make comparison, okay? So also that we have to change, convergence actually something that we discussed in chapter 1, I believe. So that we have them as the velocity is given into 80 miles per hour. This has to be changed into kilometer per second. So 1 mile equals 1.6093 kilometers. So you just have to multiply 1.6093 kilometer over 1 mile, right? And 1 hour is 3,600 seconds. So so that's going to be 1 hour over 3,600 seconds. So I'm going to change kilometer per second. So in that case, the unwanted units, Miriam can correct me this because she see the units has to be canceled. So miles per miles will be canceled. Hour by hour will be canceled. So what's left is kilometer per second, which that's what we needed. So 80 mile, let me do the calculation. If you have a different answer, you let me know, okay? So 80 mile times 1.6093, 128. I divided that by 3,600 seconds. So I would get a 5.793. Can you agree with me? Can you agree with me? So 80 times 1.6093, 128 divided by 3,600. What? I need your help. I got 0.035. What's wrong? If you change 80 miles per hour to kilometer per second, right? This is how the convergent factor works. So 80 times 1.6093. Wait a minute. 80 times 1.6093. So that gives me 10,299.50 divided by 3,600. I don't know about you, but I got 2.86. 2.86 kilometer per second. Kilometer per second. So now we can do the kinetic energy. Here, the kinetic energy is the 1/2 m times v squared, 1/2 times the mass, which would be 71.3 kilogram. The velocity is 2.86 kilometer per second square. Okay, don't forget to use your calculator. 71.3 divided by 2, that gives you 71.3 divided by 2, that is 35.65. So 2.86 squared, that means you multiply 2.86 times 2.86, that gives you 8.17. So times 35.65, so that gives you about 292 joules. That's the kinetic energy of the automobile that weighs 157 pounds and traveling 80 miles per hour. So it has about 292 joules of energy. Know how to calculate the heat loss or the heat gain? I already gave you an example of that. There's another practical problem here. Calculate the amount of heat, which we already have done earlier. The following types of radiation, frequency of wavelengths. What is the frequency? This is basically from your research paper. Actually, you can answer those questions about what does frequency means? What does what's the nature of light? The formula for the formula for electromagnetic radiation, or the wave nature of light, which is the speed of light, which is the wavelengths times the frequency. Well, here the questions maybe which one of the following is incorrect subshell notation. Maybe this might give you a good explanation for that. The subshells are where you find the number of electrons. For example, the first shell has one subshell, which is only one S. Subshells are most likely where the electrons are located. The second shell has two subshells, which is 2s and 2p. So remember that here on the second shell, there is no 3D, okay? S, P, D, and F are like their subshells found in a different shell numbers. In the first shell, you'll only find, yes, Abimola.
What sort of, can you give us examples of questions that will come from this? Because some of these that we haven't really done in class, when questions come from them, they may come in a way that, will throw everybody off their feet. So,
okay.
Yeah, what kind of questions can come from this?
Okay, great question. Okay, does the second shell contain a D subshell? Is there a possibility that this second shell contains a D subshell? What is your answer?
Yeah, that'd be no.
Yeah, that would be no. That's one question. Now, the S, the P, the D, and the F, these are the orbitals. S has one orbital, P has 3 orbitals, D has 5 orbitals, and F has 7 orbitals. Okay, so that the Pauli electron configuration rule says that each orbital holds 2 electrons, the maximum. So how many electrons you expect in the S subshell since it has 1 orbital?
That'll be 2.
How many electrons you're going to expect from the p orbital? The maximum, because p has 3 orbitals. Each orbital holds 2 electrons.
That'll be 6.
How many electrons, the maximum you expect from the d orbitals?
10.
And how many electrons you expect from the f orbitals?
That'll be 14.
Yeah.
But so these are the only kinds of questions that come from this.
No, these are some examples. Also the nature of light, like
No. I mean concerning the orbitals.
the
You know,
orbitals.
the reason
Yes,
I'm
yes,
asking.
yes, yes.
Okay.
Yes.
Okay. Because there are many other questions that can come out, so that we know exactly, exactly what.
Let me. You cut me off. Abimola. Yes. I'm also like yes. This is a picture. This is a diagram right here. So like, okay, here, for example, how many total electrons that you have in the second energy level? Okay. How many? Okay. How many?
That'd be.
How many total electrons?
That'd be 8 altogether.
Right. How many total electrons you will have in the second energy level? You already answered that. It's going to be 8. How about in the third energy level? Because 3s, 3p, 3d, it has 3 different orbitals.
That'd be 18.
In the fourth energy level?
32.
Yeah. Okay. Does the third energy level can hold 16 electrons?
16, yes.
Mm-hmm. Yes. The answer is yes. This number are maximum numbers. All right. The only problem that the third energy level doesn't have a space to hold more than 18. All right. If I ask you in a different format, that does the third energy level holds 19 electrons, the third energy level? Can it hold 19?
No.
No, the answer would be no, because the maximum number it holds is 18. This is the kind of questions that you expect. Does that make sense, Abimola?
Yes, it does.
Okay.
And then I want to just make an observation too. This type of, like this SPDF, this breakdown, there's no way we can include all of this in the research paper and still come within the maximum number of pages we're supposed to have.
No, you don't have to. You have to use just this one here. You don't need to. Yeah, you don't need to include that in the research paper. You just can use this slide right here.
Okay.
Okay. You don't have to include those. You just include the electromagnetic radiation, the theoretical perspective. That's all I need. Know the properties of the elements in a group or a period. Which of the elements would you expect to have a similar chemical properties? Now, groups are vertical columns, right? Period in the periodic table are horizontal row, right? So elements in a group, they always possesses the same similar chemical property. So you need to have your periodic table anyway in front of you when you do the exam. So you have to identify for example, here lithium and beryllium. Do they have the same characteristics? I cannot tell you because I don't have a periodic table in front of me. If they are in the same group, yes. Oxygen and sulfur, for example. Oxygen and sulfur would be yes, because they are in the same group. Iron and neon, no. Iron is a metal, neon is a non-metal. Oh, xenon and radon, yes, because xenon and radon, they are noble gases. They are in the same groups. Learn about the atomic radius, whether about the atomic radius decreases or increases as we go down to the group or from left to right. So if you have lithium and rubidium, for example, lithium and rubidium, they are in the same group. They are in group 1. So as you go down, the size increases. I think we discussed about this somewhere. The size increases as you go down in the group. As we go down to the group, size increases. Okay, so rubidium is larger than lithium because of rubidium. If you look on the periodic table, it's on the bottom. As you go from left to right, the size shrinks, the size decreases, because this is something that you answer by looking of the periodic table. So calcium versus chlorine, for example, which one is larger? So again, you're going to look to chlorine. Chlorine is smaller because chlorine is found on the right side. Chlorine is smaller due to the larger number of protons. If the proton number is adding, there's going to be a big attraction of the nucleus will be, it's called a nucleus effect. That's called a nucleus effect. Somewhere, maybe if you would like to make a search on that, you can write a nucleus effect. I don't know if that is also included in your search project, but a nucleus effect means that, let me just, because nucleus would be, if the number of proton is higher, it attracts, it shrink down the electrons in the outermost shell, so that makes the atoms will be shrinked. So that is related with the nucleus effect. Maybe some of you are very rational. You wanted to know the reason why it is that. So I would tell you that's a nucleus effect. And you know, simply you can look up on the left to right. If you look left to right, chlorine is on the left versus calcium. So chlorine will be on the right, so it's going to be smaller than calcium. Learn the difference between metallic oxide and non-metallic oxide. We discussed about this. Metallic oxides like sodium oxide, potassium oxide, these are metallic oxide due to the fact that they're made from metal. So how do we identify metallic oxide from non-metallic? That metallic oxide, when they react with water, they form alkaline solution. Non-metallic oxide, when they react with water, they form acidic solution. You just write here. So that's how you, non-metallic oxide, when they react with water, they form acidic solution. These guys, they form alkaline solution. So that's how metallic oxide difference from a non-metallic oxide. Okay, like nitric acid and sulfuric acid. By the way, these are a formation of acid rain. Remember, acid rain and pure rain. Sodium bicarbonate, baking soda is a weak base. Identify weak base versus strong base. We discussed about that earlier when we discussed about acid and bases. So this is pretty much it. So what I'm going to do, let me save this because this is upgraded now because we added new things. We made corrections also. So I'm going to, okay, correct that. I'm going to post this now as a review guideline, and then a video, and then the exam will be next week at the same time. It starts from 6 to 8:30. Susan?
Hi, good evening. I apologize if you answered this already, but this is a final exam, so it's cumulative, correct? It's from everything that we learned from the first day?
Susan, a little bit slower. I cannot hear you. Can you be?
Yeah, hi, sorry about that. This exam will, because it's a final exam, will it include chapters 1, 2, and 3? I apologize if you went over that already, but I don't remember hearing if it will or not cover it.
No. Okay. It's pretty much, I don't know if you think that it includes chapter 1, chapter 2, chapter 3, but it's okay. The most component is like 3, 4, 5, especially 3 and 4. However, like when you do conversions, right, Susan? When you do conversion, like for example, if I have asked you a conversion factor to change pound to kilogram, kilometer to hours to second. This is something that we discussed in chapter 1. There may be 1 or 2 questions, just like the kinetic energy example I showed you earlier. But the significant part of this is exactly what is here. So
Okay.
this is your GPS right here, Suzanne.
Okay, fine. I just didn't know if that was just the new information.
Yes.
And also,
yes.
do you know how many questions?
I'm working on it. I believe it's going to be anywhere between 40 to 50 questions.
Okay.
I'm working on it.
Okay, thank you.
Mm-hmm. Suzanne? No, sorry, Abimola?
Yes, 2 questions actually. First is this going to be set by the department, or are you going to set your own questions?
I'm going to set my own questions. However, we have embedded question included here. The embedded question is a question that we all have to use by our own. So out of this question, there are embedded questions, but included here, as I discussed. There might be questions from acid and base. There might be a question from molarity. There might be a question for relative concentration, or it is a oxidation reduction reaction, but the embedded questions are included here.
Can you say what percentage will be the embedded questions?
No, they have the same equal pointers.
Okay.
Embedded question is for us, for teachers, to make an assessment.
Oh, I see.
Yeah, not for you guys.
Okay. Then the final question is, how long are we going to, you say we're going to have about maybe 40 or 50 questions. How long are we going to have to
I will
finish
calculate after I made the questions. I will calculate that and I'll post that for you.
Okay.
So I'm going to make a quick attendance while you are here. That makes things easier for me. And then I will post the updated version of the review guideline after we finish this class, and I'll post the explanation. And I wanted to say thank you for everything. Thank you for your patience. And I wanted also to say thank you for today that you're waiting me. And it was a great class. And if you have any questions between today and next week, please, you can text me at this number and we can discuss questions that you may have. Abimola, you still raise your hand, or is this from the previous hand?
Oh, that's from the previous one, sorry.
Okay, Vivian, okay, I see Vivian.
Professor, yes,
Vivian.
my attendance, I have a problem with my attendance, both lecture and lab. I don't know what's happening, but I've not missed.
Let us talk after class, please, okay? Let me take the attendance. If it is your problem, let us talk after class, okay? You use this number, Vivian, and call me, and we have to figure out the date when you had a problem. I see Kalala, you raise your hand.
Yes,
Professor,
Professor, my question has to do with the research purpose, because when you were talking about the electron on the shares, you were saying that this. Now, what are the points that you want necessary to see on that research papers? Because it seems like when you were saying that you will mention this, it seems like there is something that you want specifically to be on that paper.
Okay, I don't remember on the top of my head, but mostly what I'm looking for is that the electrons are considered as a wave functions. The electrons have electromagnetic radiation properties. Sometimes electrons have a dual nature, which means that they're considered as wave, and they also be identified or explained as with the density of population. We're not like counting electrons, truly speaking. Did I give you the skeleton of what has to be written, what is needed on the as a guideline for your research paper?
No.
That's the main things that I'm looking for. You don't have that?
No, we don't have that guidelines.
Uh-oh.
You said that we have to read chapter 6.
No,
and then 7 and a summarize, but there is no guideline.
I do remember
no, I put a guideline. I put a guideline. What is the index number of your course?
Is it 3850?
3850. If I didn't do that, that's really a big mistake. Hold on. Because I gave
it's in the announcements.
It's on the announcement, yes. If it wasn't the announcement, the breakdown is there. I post that to everybody. A research guideline. Thank you very much. So it is there. You can look at it. So that's the main point that I'm looking for there.
Okay.
Look on the announcement area. Okay, let's.
So when is it due?
Well, we were discussing, it was today, right?
Yeah, but I talked to you
No,
yesterday.
you said the
you were
10th.
You said the 10th.
The 10th.
Okay, all right, okay.
I talked to you
Keep my
yesterday.
promise. Let's do 10 midnight.
Okay.
All right, let's do 10 midnight. Now, please do me a favor. Send me to wendeson@hotmail.com. Okay, and CC to wfikra@bccc.edu by December 10 midnight. Okay, send me to this address and CC to wfikira@bccc.edu. So let me just take a quick attendance before 3850. If you cannot say yes, text me a text message, then I can able to identify who you are. I have my tablet here with me. I can able to see you, okay? Sydney, about Sydney, Daniel, Adekuni, Daniel, Opiemi, Alo.
I'm here.
Okay, Angie, Alva, Angie.
Here.
Okay, Ababech, Azaza, Abimola.
Yes, I'm here.
Isatu, Ba.
Yes, I'm here.
Okay, Miriam, Bernabum, Miriam. Miriam was here, right? Miriam?
Yeah, Miriam is here. I see her. I don't know.
Miriam, where are you? Jasmine, Blanding? If you cannot talk, text me a message. Jasmine?
I'm here.
Okay, thank you, Jasmine. Melvin Daniels? Melvin? I saw Melvin earlier.
Yeah, he was there.
So when maybe you guys have, if you have issues of communicating, text me. Chelsea, I don't want you to make absent while you are here. Chelsea, Adhanet, Adhanet. Adhanet, okay, Adhanet, you raise your hand. I think that's the way. Maybe you cannot able to talk. Kalala?
Yes, I'm here.
Okay. I see you, Adhanet. I see you. Okay. I think I understand. Susan? Susan Kat?
I'm here. I'm
Okay.
here. Thank you.
Vivian Kimby?
Yeah.
Nicole? Nicole McLean? Nicole Morant?
Yes.
Okay. Ada Obiora?
Here.
Okay. Now, who's Dobies? Who's Dobies?
Here. Adobe.
Okay.
I have a question. Is the final going to be in the Lockdown browser next week?
Yes, yes.
Okay.
Adobe, okay. Anastina Ogobi? Anastina? Ifoma?
Yeah, Professor.
Ifoma, okay. Nicholas Perry? Nicholas Perry? Nicholas Perry. Elder Stemba? Okay. Did I miss someone? Or if you cannot able to talk, raise your hand so that I can able to identify you. Or text me a message. Or text me on my number if you are here now. Okay. I'm going to send you the video and the upgraded version shortly, okay? Thank you everybody, and thank you for the entire semester. I will see you next week, but any questions that you have, text me and then we'll discuss, okay?
Bye.
Okay, fine.
Okay, have a nice evening, everybody, and I'll send you shortly. Let me see if, okay.
Thank you so much.
Thank you, everybody.
Thank you, Professor.
Thank you, everybody.
Bye.
Thank you for all your patience. I appreciate
Thank
that.
you for everything.
Thank you. Good night.